to find they asked us to find the resultant force or the frictional force in the very first part of the question, using three other forces that were being applied. But in that part, they didn't use the mass into gravitational force as a force to find out that resultant. But when we had to use it, when we had to do the second part, which included us using Newton's second law, which resultant force is equals to ma, then we use the mass. So is mass negligible when they've not mentioned that we're supposed to take weight and asking us to find a resultant?
Okay, so I think this can be best answered by looking at that example. I think I kind of understand what you mean. Probably the question would have a statement like this, that the forces are horizontal. Does it say something like that?
A small block of mass 1.25 kgs on a horizontal surface, three horizontal forces.
Yeah,
Yes, sir.
yeah. So, okay, so let's talk about that. So let's start with that question and any other questions that other people have. And then we would look at the two questions that I'm talking about. All right. Just give me a minute. Then we'll start. Newton's second. Okay, so can you tell me the question number that you're talking about? Is it from the friction worksheet as well?
Yes, sir. There's question number 56 and 32. They're both the same in this matter.
Okay, so let's have a look at one of them. Okay, so you're talking about question number 32, first of all? Okay, let's have a look at this. Okay, question number 32 from the worksheet. A small block of mass 1.25 kilograms is on a horizontal surface. Okay, it's on a horizontal surface. The mass is 1.25 kilograms. Three horizontal forces. So the surface is horizontal, and the forces that we're talking about, they're also horizontal. And they have these magnitudes and directions as shown in the diagram. So all of these forces are horizontal. Then applied to the block, the angle theta is such that cos theta equals 0.28, sine theta equals 0.96. A horizontal frictional force also acts on the block, and the block is in equilibrium. So there's a frictional force that's also horizontal along the surface. That's also acting on the block, and the block is in equilibrium. We need to show that the magnitude of the frictional force is 7.5 Newton and state the direction of this force. Okay, so we have these three forces, and there's going to be some friction somewhere. We don't know where exactly that is going to act. We need to find the magnitude of the frictional force. Now, if you think about it, if the block is in equilibrium, that means all forces should be balanced. Forces acting towards the left, they should be equal to forces acting towards right. Upwards forces should be equal to the downward forces. So we just have to equate the opposite forces. But first of all, we need to consider all the forces that are acting in this particular case. Now, three forces, they have told us that these are three forces that are acting. And then you're basically saying, what about the mass of the object? Since the mass is 1.25 kilograms, that means the weight of the object is going to be 12.5 Newton. And you might think the weight of the object should also apply vertically downwards in this direction, that is 12.5 Newton. And that is what you're confused about. Why are we not considering this? The thing is, it's a horizontal surface. That's what they've told you. It's a horizontal surface. So think of a horizontal table. Okay, think of a horizontal table. Let's say you have a snooker table, right? You have a snooker table and you have some balls placed on that table. So let's talk about one ball in particular. That ball has some forces acting in horizontal direction along the snooker table. So you have one force acting. So let's say this is the ball. You have one force acting to the left side, and all of this is happening on the table. All right. You have one force acting in one direction, upward direction on that table, and you have another force acting at this angle, 5 Newton. Where is the weight of the ball going to act? Weight of the ball is not going to be on the same plane as the table. Weight of the ball is going to act vertically downwards. So if you were to consider this screen as that table, screen as the table, all of these forces are on this screen. Okay, all of these forces are on the screen. Weight is going to be going inside the screen, into the screen, vertical to all of these forces, perpendicular to all of these forces. Weight is going to go into the screen. If all of these forces were part of the screen, weight would be going into the screen. That's what the difference is. So weight is not in the same plane as the other three forces. Now, my drawing is not that good. Let me see if I can maybe try and show that to you like this. So this is what the table is. Table looks like. Weight is going, how do I show this? Weight is going vertically downwards. Basically, this is perpendicular. This is 90 degrees. This is 90 degrees. And this is 90 degrees. All those forces have a 90 degrees angle with that weight. And that is going into the screen. Does that make sense?
Yes, sir.
So that is why when we are considering the forces acting along the surface, we are not considering weight. So that basically is clear then that we are not going to be considering weight in this case, because that's going into the plane. The fourth force is friction. And because of friction, the object is in equilibrium. Now, where should friction act if it was to remain in equilibrium? It should be somewhere on the right side, right? It could be here, it could be here, it could be here, right? It's clear from the diagram. It should be in one of these three directions. Either it could be horizontal to the right, or it could be here, or it could be here. It could be any of these directions. Okay. Now, one way of thinking about this is that you find the resultant of the other three forces. That will be something on the left side. Friction will be exactly opposite to that. Or another way to think about this could be wherever friction is. We don't know where exactly what exactly the direction is going to be. Let's say this was the direction of friction. Let's assume this is the direction of friction. Then it would have some x component. Let's call that fx. And it would have some y component. Some horizontal component, some vertical component, fx and fy, right? What we can do is we can find the values of fx and fy, and that will tell us the overall friction's magnitude as well. If instead of this direction, you say, okay, what if the direction of friction was this? Why are we considering fy there? Well, that's still going to work, because if the actual friction direction was this one, then that Fy would turn out to be negative. And that would make us understand, okay, the actual direction was this and not this. So all you have to do is take one horizontal component of friction and take one vertical component of friction. Fx and Fy. Okay, I'm sorry about that. So take one horizontal component, take one vertical component, Fx and Fy, and now you just equate the opposite forces. And you will find the value of Fx and Fy from that. Let's see how we can do that. 4.8 and 6.1 are already vertical and horizontal. We don't have to resolve them. We can resolve the other forces. 5 Newton, we can resolve this force. If this angle is theta, we're going to have two components of 5, one towards the left side. That's the component adjacent to the angle. That's going to have 5 cos theta. And the other component on the other side of the angle, that's going to be 5 sine theta. These are the forces that we have. We just equate the opposite forces. We say 6.1 plus 5 cos theta should be equal to Fx. And Fy should equal Fy plus 4.8 should equal 5 sine theta. That's all that we've got to do. Let's do that. Equate the forces acting towards the left side to the forces acting to the right side. Equate upward forces to the downward forces. On the left side, we have 6.1 and 5 cos theta. To the right side, we just have Fx. Upward forces Fy and 4.8. Downward is 5 sine theta. Now we have cos theta and sine theta values given in the question. Cos theta is 0.28, sorry. So it becomes 6.1 plus 5 into 0.28. That equals Fx, right? That will give you the value of Fx. What's that?
So Fx is 7.5.
7.5 Newton. And then Fy equals 5 into 0.96 minus 4.8. What about that?
0.
This is 0. So that means there's no vertical component of friction. And there's only horizontal component. That basically tells us the friction has a magnitude of 7.5 Newton. What about the direction? It's towards east. You can say east or you can say right. Both of them are okay. There's no angle involved, so you can just write this. And towards the right side, or you can say towards east, that's friction. That's the first part. Okay. Then it says, given that the block is in limiting equilibrium, find the coefficient of friction between the block and the surface. Now, what does limiting equilibrium remind you of? Whenever you see limiting equilibrium, that should remind you of F equals mu r. All right, F equals mu r. Now, friction is 7.5. It says it's in limiting equilibrium. If it's in limiting equilibrium, F equals mu r. What we need to find is the coefficient of friction. Do we have the value of r? Well, think about this. We had this horizontal surface. Yeah, so we can actually draw it like this. This is the horizontal surface. This is the particle. And weight is applying vertically downwards. Weight is applying vertically downwards. Where is reaction going to act? Reaction is going to act vertically upwards. Now, perpendicular to this table, there's no other force acting. Why is this so slow? Okay, so perpendicular to the plane, there is no other force acting. There's just weight of the object, which was 12.5 Newton, right? All the other forces are horizontal. They are along the table. Perpendicular to the table, there's only weight. So reaction is going to be opposite to that. The value of reaction is also going to be 12.5 Newton. And we can just input those values here now. We can say F equals 7.5, that equals mu into R. R is 12.5, and mu equals 7.5 over 12.5. What's that?
0.6.
0.6. That's the coefficient of friction that we were looking for. Okay. Let's look at the third part now. Now, what does the third part say? It says the force of magnitude 6.1 Newton is now replaced by a force of magnitude 8.6 Newton, acting in the same direction, and the block begins to move. Find the magnitude and the direction of the acceleration of the block. Okay, so now instead of the 6.1 force, we have an 8.6 Newton force acting towards the left side. Now, what happens when you have this 8.6 Newton force? Remember earlier, the block was in equilibrium. The block was not moving. Okay. In fact, it was in limiting equilibrium. In the second part, we also know that now. It was in limiting equilibrium. That means if we were to apply even slightly more force now, the object is going to start moving. Right? Now, when this force was 6.1 Newton, the block was not moving. It was in limiting equilibrium. When you replace 6.1 with 8.6 instead, the block is definitely going to start moving. What is going to be the resultant force? The resultant force earlier was 0 because the object was in equilibrium. On the left side, now you have changed the 6.1 force to 8.6 Newton instead. That means the left force has increased by 2.5 Newton. So what is the resultant force going to be? You don't need to do any of those calculations again. It's just easy to understand from that directly that earlier all the forces were in equilibrium. Only thing that has changed is this. There's a 2.5 Newton force acting towards the left side, which is the resultant force. So resultant force is 2.5 Newton that is acting towards the left side here. What we need to find is the magnitude and direction of the acceleration of the block. Now, if we know this is the resultant force equals mass into acceleration. Resultant force is 2.5 Newton, considering the left side positive. Why? Because the object is going to move towards the left, since the force acting towards the left side is greater. 2.5 equals mass, which is what 1.25 into acceleration, and that's going to give you acceleration equal to 2 meters per second square. And they also asked us for directions. We have to write it explicitly. It's towards the left side. That's the acceleration and the direction of acceleration. Make sense?
Yes, sir.
Okay. All right. Any other questions? Any other questions from the worksheet apart from this?
Question 14, sir.
Question number 14. Okay, I'm just checking my connection again. Can you still hear me? Because I think the other device is not working.
Yes, sir, we can hear you, but the iPad screen is not moving.
Okay, all right. Yes, so what was the other question that you said?
14, sir.
14. Okay. The rest of you don't have any questions? Where does it start? This is 13. Okay, maybe it's just not visible. Okay, this is the one, right? Question number 14.
Yes, sir.
Okay. You have any other questions apart from this as well?
No, sir.
Okay, so after this, we'll do those two questions that I wanted to do today. They have, both of them have something slightly different to what we've done until now. But let's do this one first, question number 14, and then we look at those other two questions as well. Okay, so it says a rough inclined plane of length 65 centimeters is fixed with one end at a height of 16 centimeters. Above the other end, particles P and Q of masses 0.13 kg and 0.11 kg respectively are attached to the ends of a light and extensible string which passes over a small smooth pulley at the top of the plane. Okay, so we can see these two particles. One particle is here, another is here. It's a rough plane. That means there's going to be friction. 65 centimeters and 16 centimeters are visible on the diagram. Their masses are 0.13 kg and 0.11 kg respectively. There's a smooth pulley on top of the plane. Particle P is held at rest and particle Q hangs vertically below the pulley. The system is released from rest. Now, when the system is released from rest, P starts to move up the plane. P moves up the plane. Draw a diagram showing the forces acting on P during its motion up the plane. Okay, so basically we just have to represent all the forces acting on the object P, on the particle P. What are the forces acting on particle P? We have weight of P that's going to act vertically downwards. What's that? That is 1.3 Newton, right? 0.13 into 10. Normal reaction, that's going to be perpendicular to the surface like this. This is normal reaction. What else? We have tension. It's tied to a string, so tension is going to act away from P in this direction. And then we have friction because it's moving up the plane. The plane is rough. Friction is going to be acting in this, going to act in this direction. And that's it. These are the forces that we have, right? So that's the first part. Now it says show that T minus F is greater than 0.32, where T is the tension in the string and F is the magnitude of the frictional force on P. T minus F has to be greater than 0.32. Now, the particle is moving up the plane. Since the particle is moving up the plane, its forward force has to be greater than the backward force, right? The forward force, T, that has to be greater than the backward force, which is which is friction. Now, this is saying the difference between T and F, that should be greater than 0.32. Now, how do we think about this? What are the forces acting on the object Q? The weight of Q is going to be 1.1 Newton. That's the force acting vertically downwards on Q. And what about the tension? Tension is going to be in this direction. Okay, so how do we think about this? The forces acting in the direction of motion, they should be greater than the forces acting against the motion. That is when the object is going to move in that direction, right? So what can we say? We can say, let's resolve the forces that we have. First of all, acting on P, we have the forces acting on Q already on the side. What are the forces acting on P? We have represented these forces as well. However, weight is not resolved yet. So we first resolve the weight in this case. Let's see what we get when we resolve the force. Resolve the weight. This is 1.3 Newton. It's going to have two components. One component is going to act in this direction along the plane. This is one component. And one is going to act perpendicular to the plane. That's going to be in this direction. These are the two components of the weight. Now, if this angle of the plane was theta, then one component would be 1.3 into cos of theta, because this angle would also be theta. And the other one would be 1.3 sine theta. All right. These are the two components of weight. Now we just need to say that since the particle P is moving up the plane, the force T should be greater than friction plus 1.3 sine theta. So force T has to be greater than friction plus 1.3 sine theta. Okay. Now the problem is we don't have theta. How can you find theta now? Now for that, they have given us this length. This is 65, this is 16. We can use these lengths to find the value of theta. We can make a right angle triangle, right? We have a right angle triangle like this. We have a vertical side, which is 16 centimeters. We have this slanted side, which is 65 centimeters. We can find this theta, right? So what ratio do we use? We can use sine perpendicular over hypotenuse. Sine theta equals 16 over 65. Now, it actually turns out we have to use sine here. So we don't necessarily have to find the angle, just leave it in sine form. Sine theta equals 16 over 65. We can use it as it is in our working. Now, since the particle is moving up the plane, that means the forces acting up the plane, what are those forces? There's only one force, P. That should be greater than the forces acting down the plane. So we have friction and we have 1.3 sine theta. So that means T minus F minus 1.3 sine theta, that should be greater than 0. Or we could also think of it this way. We could say T is greater than F plus 1.3 sine theta. Make sense? Only then the object can move up the plane, when T is greater than the forces acting down the plane. Now, what does that give you? T is greater than F plus 1.3 into sine theta. What's sine theta? Sine theta is 16 over 65. You can see what this turns out to be. T greater than F plus 1.3 into 16 over 65. What's that?
0.32.
0.32. And that's what we had to show here. We can just take friction to the other side. Now, they have represented friction with capital F. So we can say T minus F is greater than 0.32. Now, if friction was capital F, we can say T minus capital F, that is greater than 0.32. That's what we had to show in the second part. Okay. Since the particle was moving up the plane, that means the forces acting up the plane have to be greater than the forces acting down the plane. That's what we did, and we got to that inequality that they asked us to find. All right, now it says the coefficient of friction between P and the plane is 0.6. Find the acceleration of P. Okay, so now we need to find the acceleration of P. What we can do is we can apply the Newton's second law of motion. I'm sorry, just give me a second. Okay, so what we can do is we can just apply Newton's second law of motion in both of those objects one by one. So we have two objects, one is P and the other is Q. This is P and this is Q. P is moving up the plane, so we take that direction as positive for P. Q is moving down, vertically downwards, we take downwards as positive for Q. Now for P, what's the forward force and what's the backward force? Forward force is T. So we say T minus backward force is F and 1.3 sine theta. That's 0.32. We've already found that. Write that again if you want. 1.3 sine theta. This should equal mass of P, which was 0.13 times acceleration. Now that gives us T minus F. Now, since the particles are moving, when the object is in motion, friction is at its maximum value. So we can replace friction with mu r. We can say friction is mu r minus 1.3 into sine theta. Sine theta is 0.32. Sorry, the result from this was 0.32. Let's write that here directly. That equals 0.13 times A. Mu is given to be, mu is what, 0.6 into R. Now, what about R? Remember, when a particle is moving along the surface, the forces acting perpendicular to the surface, they're always equal to each other. So reaction is supposed to be equal to 1.3 cos theta. Now that can be found by finding theta first of all here, and then finding cos theta, or you could use that right angle triangle to find base for this triangle as well. So let's try doing that instead. Let's find the base, in fact. What do you get for that? 65 squared minus 16 squared. And then square root of that. Can you tell me what that is? Base square equals 65 squared
63.
minus 16 squared. The base turns out to be 63. If base is 63, that means cos theta is base over hypotenuse, that's 63 over 65. So we have the value of cos theta. So that means it's R is equal to 1.3 into 63 over 65. What do we get from that? 1.26.
So 1.26.
1.26. 1.26 Newton, that's the value of R that we have. So 0.6 into 1.26 minus 0.32, that equals 0.13 times A. This is one equation that we've got. T minus this, 0.6 into 1.26 plus 0.32. What do you get from that?
1.076.
1.076, that equals 0.13 times A. Similarly, you get another equation for Q. Q is moving down the plane. What's the forward force for Q? 1.1. What's the backward force for Q? It's the tension. 1.1 minus T, that equals mass of Q, which is 0.11 times A. You have two equations. You can eliminate T from them. T equals 1.1 minus 0.11A. And from the second equation, we get T equals 1.076 plus 0.13A. These 0.13A. And that gives us 1.06 plus 0.13A. That equals 1.1 minus 0.11 times. And that will give you the value for acceleration. What do you get from this? What's the acceleration?
0.1.
0.1. 0.1 meters per second square. Okay, that's what we were looking for. That's the third part. Any problem with this?
No, sir.
Okay, good. Now let's look at a couple of other questions before we end this topic, before we wrap this topic up. Okay, so these two questions. All right, so let's have a look at this one. It says on a straight horizontal test track, driverless vehicles with no passengers are being tested. A car of mass 1600 kg is towing a trailer of mass 700 kg along the track. the brakes are applied, resulting in a deceleration of 12 meters per second square. The braking force acts on the car only. In addition to the braking force, there are constant resistance forces of 600 Newton on the car and 200 Newton on the trailer. Find the magnitude of the force on the tow bar. Okay, so we don't have a diagram here, so we're going to draw a rough diagram to understand the situation better. So we have the straight road, and on that road, we have a car and a trailer. I'm just going to represent them using these boxes. My drawing is not very good. So let's say these are the car and the trailer. So car is towing the trailer. So car is ahead. So if they are moving in the right direction, car is on the right side, and then it has a trailer tied to it, connected to it. It has a trailer connected to it using a tow bar, right? Okay. So we have this tow bar, and the car and the trailer are connected using that. Now what's happening is mass of the car is 1600 kg. That's one thing that we're given. The mass of the trailer is 700 kg. We can find the weights for both of them using this if we had to, but weight is acting vertically here. The movement is horizontal, so weight does not really contribute to their motion as such. So let's not represent them for now. The deceleration is 12 meters per second square. The braking force acts on the car only. When the brakes are applied, the braking force acts on the car. So basically, the car was moving towards the right side, and then brakes are applied. Now, when brakes are applied, of course, there's going to be no driving force as such. There's going to be no force on the right side, because when you apply brakes, of course, you are not going to have your foot on the accelerator as well at the same point, right? If you do that, you should not do that. When you apply the brakes, you do not have your foot on the accelerator. So there's no driving force. There's only a braking force. Where does that act? That acts in the backward direction. So there's a braking force acting on the car that has a magnitude of, we don't know that. Let's call this B, the braking force. In addition to the braking force, there are constant resistance forces of 600 Newton on the car and 200 Newton on the trailer. So there's a force acting towards the left side on the car that has a magnitude of 600 Newton. This is the resistance on car. And on the trailer, the resistance is 200 Newton. Now, this resistance could include friction, air resistance, whatever. All of that is included here. All right. Now, these are the forces. These are all the forces acting on the car and the trailer. We also have tension, by the way. If you think from the perspective of the car, where is the tension going to act on the car? On the car, the tension is going to act away from car in this direction and towards the tow bar. That's what we say. That's what we're used to doing, right? For a string, what do we do? We say the tension acts away from the object and towards the string. So this is going to be the direction of the tension. That's what we consider for the car. And for the trailer, we say the direction of tension should be this one. These are the forces acting. We are given deceleration. We are supposed to find the magnitude of the force in the tow bar. So basically the value of this T. How do you do that? You can apply Newton's second law of motion. You can say resultant force equals mass into acceleration. Movement is towards the right side. What's the forward force? There's no forward force. So let's apply Newton's second law of motion separately to car and the trailer. So for car, we can say there's no forward force, right? There's no forward force for car. Now it's still moving towards the right. Why? Because let's say you're moving at 100 kilometers per hour. When you apply brakes, you don't stop immediately. It takes time to stop, right? So from 100 kilometers per hour, it's going to reduce to 99, 98, 90, 80, 70, and so on. While that happens, you are still moving forward, right? So the car is still moving towards the right, but there's no driving force. It's just moving because of the velocity it already had before the brakes were applied. So what's the forward force? There's no forward force. What's the backward force? There are three backward forces. We have resistance, that's 600. We have the braking force, B, and we have the tension, That equals mass of the car, which is 1600, sorry, into acceleration. And the value of acceleration is negative 12. There's a deceleration of 12, right? That means acceleration is negative 12. So we have this equation for car. Okay, what do we get from this? Minus 1600. In fact, we have two unknowns here for now. Let's look at trailer. What are the forces acting on the trailer? Forward force is T, and backward force is 200, and that's it. Mass of the trailer is 700 into acceleration, which is negative 12. This only has one unknown, T. We can find the value of T here. Let's see what that turns out to be. T equals minus 8400 plus 200. The value of T turns out to be negative 8200 Newton. Now, the point of showing this question to you was that you can sometimes get a negative value for tension when you use the methods that we have learned. And that's perfectly okay. This is exactly how you would do it. What's happening is we took the direction of tension like this, that it acts away from the car and towards the tow bar. And that's what we normally do for strings. Now, in this case, it's not a string, it's a tow bar, but our method is going to remain the same. We still do the same thing. We say, we will do the calculation using this, that we take tension to be on the left, to be acting on the left side on the car. And similarly on the trailer, we would take the tension to be acting on the right side, like we normally do. But the value of tension at the end is turning out to be negative. That basically tells us that the actual direction for tension on the trailer is this, and the actual direction for the tension on the trailer, tension on the car is this. Now, why is that? It's a tow bar. Tow bar is something rigid. Think of it as a rod, for instance. When you apply brakes, when the car applies brakes, when the brakes are applied on the car, what happens? Car starts to decelerate, its velocity decreases. There are no brakes applied on the tow bar, right? Tow bar is not something that has any intrinsic force as such. Brakes are applied on the car. Tow bar was still moving at a greater velocity. So tow bar is actually going to push the car. When the car applies the brakes, tow bar is going to push the car forward. Because of that, the actual value of the actual direction of tension is going to be to the right side. And similarly, it's going to push the trailer backwards, okay? Because when the car stops, it's going to make the tow bar stop as well. Because of that, the tow bar is now going to stop the trailer as well. So the the force on the trailer by the tow bar is going to act towards the left side. So the actual directions are opposite to what we have taken here. That is why the result is turning out to be negative. And that's perfectly okay. You will do it exactly like we have done here. Since they were asking for the magnitude of the tow bar, magnitude of the force in the tow bar, you would say magnitude of the force in the tow bar. Magnitude is something that's positive, right? You would say magnitude of the force, that is equal to 8200 Newton. The final answer, you'll just write positive, and that's going to be okay. Now, why is it happening? We are used to talking about strings, and that's what 95% of the questions are about. They have strings. Now, when you have a string tied to an object here, a string can only pull objects, right? The string can only pull the object towards itself. It can't push the object towards the right side, right? String is not rigid. It can't push the object towards the right side. String can only pull things. So because of that, we always take tension direction to be like this. But if you have something rigid, if you have a tow bar in this case, or a rod, for instance, If a rod was tied to an object, a rod can both pull the object and push the object. It can do both things. So in this case, tension could act in this direction or in this direction. Both possibilities exist. What we are going to do is, we are going to do it the way that we are used to doing everything. Take the same direction that you take for strings. If it is the other direction, it would automatically turn out to be negative, and that's perfectly okay. This force that is applying towards the right side, it's actually called thrust. That concept is not part of your syllabus. The examiner just expects you to understand that this force can turn out to be negative, and you just don't have to panic in the exam that why is it negative, maybe you're doing something wrong. If it's a rigid thing, if it's something other than a string, you can get a negative value. You can get a positive value as well. You can, tension could act in this direction as well, and you can get a negative value as well. In this case, both values are possible. So don't think that your answer is going to be incorrect in this case. If you have a rigid thing instead of a string, this is possible. Okay, so everything remains the same. All you need to remember is you could end up getting a negative value, and that's perfectly okay. Let's look at the second part now. Now, we did not really use the Carr equation as such. Now, the second equation, the second part asks us to find the braking force. So basically, this B, that's what they're asking for in the second part. Now, for that, we can use the second equation for Carr. All right, in the first part, we just used the Taylor equation. Now we can use the Carr equation. Just input values in this now. We have the tension as well. What's the value of tension that you're going to input here? The tension value that you got was negative 8200. You're going to put that same tension value that you got because you are treating the tensions to be in this direction, like you normally do. Whatever value you get for tension, whether it's positive or negative, you're going to put the same value in the other equation to find any other unknowns that you have. So the tension value is negative 8200. You would put that here. And then you have minus 12 into 1600. That's minus 19,200. Let's simplify this. That gives you minus 600 plus 8200 plus 19200 equals B, and that's going to give you the braking force. What's this?
Twenty-six thousand eight hundred.
26,800. This is the braking force, 26,800 Newton. So what you need to remember from this example is that you can sometimes get a negative value of tension as well. You will see such questions in some recent papers. There are, I think, at least 2 or 3. So you just need to remember this, okay? You could get a negative value of tension like this. Any problem with this? No? Okay, one last question. This is another type of question that you might see in some paper. Now, this is taken from some other board, I think, but it explains the concept. So let's understand this. So we have a lift of mass n kilograms being raised by a vertical cable attached to the top of the lift. So we have this cable. This cable is raising the lift. A person of mass m kg stands on the floor inside the lift. The lift ascends vertically with constant acceleration, 1.4 meters per second square. The tension in the cable is 2,800 Newton, and the person experiences a constant normal reaction of magnitude 560 Newton. So the normal reaction is 560 Newton. The cable is modeled as being light. That means you can ignore the weight of the cable, all right? The person is modeled as a particle. So that means it doesn't really matter where the center of gravity, etc. is. Air resistance is negligible. Okay, so you have to find m, which is the mass of the person, and capital M, which is the mass of the lift. Okay, so we have acceleration given. We have to find masses. Masses means we have to find weights, and then masses could just be found by dividing the weights by 10. Weight is a force. We have acceleration given, so that means we have to use Newton's second law of motion here. That's what we do. Let's apply Newton's second law of motion in both the objects. Let's talk about the person first. What are the forces acting on the person? We have the weight of the person. Where does that act? Vertically downwards. If the mass is m, what about weight? That's 10 times m, right? That's the weight of the person acting downwards, 10 times m. And then there's some reaction by the surface. Reaction is going to act vertically upwards on the person. Let's call that r. Let's call this r. R. Okay, these are the forces acting on the person. There's no other force acting on the person. Okay, what about the forces acting on the lift, on the whole system? Basically, on the whole system, if you consider this whole thing, there's tension acting vertically upwards. We know the value of that tension. That value of tension is 2800 Newton. On the whole system, as in the person and the lift combined, there's a force acting in the upward direction, which is 2800 Newton. And there's a there's going to be a downward force, the weight of both the objects together, lift and the person, right? The total system, the total weight is going to be m plus m times 10. So that's 10m plus 10m. That's the weight acting on this whole system. And we also know the reaction, by the way, reaction on the person, 560 Newton. This value is 560 Newton. Now the person is moving upwards along with the lift, of course, and the whole system is also moving upwards. We can apply Newton's second law of motion on both the objects one by one. We can consider the person only, because we have some forces given for the person. And then we could also consider the person and the lift together, because the tension is acting on both of them together. So basically the whole system, that's what we will consider in the second case. So what are the forces acting on the person? What's the forward force on the person? The forward force on the person, since the person is moving upwards along with the lift, it's moving upwards, right? It's moving from one floor to another. The forward force is 560, the reaction. What's the backward force, downward force? That's 10 times m. That equals mass of the person, which is m, into acceleration, which is 1.4. Now, the common error here is to assume that reaction and the weight of this person should be equal. If you were considering with respect to the lift, yes, you can say the upwards and downward forces are equal, but think of this standing outside. So you're standing outside here looking at this thing. The person is going upwards. Since the person is going upwards, there's some force that is taking the person upwards, right? The person is going upwards because of this force that the lift is applying on that person, that's taking him or her to the second, third, fourth, fifth force. All right. So the forward force is 560, the backward force is 10m. What does that give you? That will give you the value for m. That is 560 equals 11.4 times m. And that will give you m. What's that? What's the value of m?
$49.122.
Sorry, could you repeat that? 40?
9.1.
49.13?
1228.
1228. 49.1228. This is the mass of the person. Now you consider the whole system. If you consider the whole system, what are the forward forces? Tension, 2800 Newton. What's the backward force? These are the backward forces. 10m and 10m. That equals mass. The total mass of the system is m plus m into acceleration. Acceleration is 1.4. You can input the value of m that you found there. 49.1228 minus 10 times m. That equals 49.1228 plus capital M whole multiplied by 1.4. And that will give you the value of capital M. Make sense? This will eventually become something like this. 10m goes to the other side. We have 1.4m there. That's 11.4 times capital M. On the other side, you can say you have 2800 minus 491.228 and minus 49.1228 multiplied by 1.4. Now, can you find the value of capital M from this?
196.49.
Sorry?
196.49.
196.49. So capital M is 196.49 kilograms. That's the value, that's the mass of the lift. And that's what we were looking for, mass of the person and the mass of the lift. This is how we deal with problems like these, where you have a lift, an elevator, and inside that you have some person or some other mass. You would consider the mass inside the lift separately and then the whole system separately. You get two equations like this and then find the unknowns. Make sense? Any questions on this?
No, sir.
No? No problems? All right, that's it for today then. In the next class, we will be starting work, energy, power then. That's tomorrow. And we would try to cover both work and energy tomorrow, inshallah. If not all of it, let's see. And then you have time for practice on Tuesday. Then, inshallah, we will be doing practice questions on work, energy, and power. That's it for today. I'll see you again tomorrow. Allah Hafiz. Bye.